Okay, so, well, this requires some work. Some work.
Is this related to some other statistical computations? I mean, is it equidistributed with some other?
Next. Of course it's related, otherwise you would not compute this. Now. Okay, now I come back. Let t sub 2n plus 1 be the sequence of the tangent numbers. So usually, if you are not in combinatorics, everybody knows the first two terms. Everybody knows when they study calculus, then the tangent of u is u plus u squared divided by 3. So and then a few people know this one. Very few, some of them. Forget about those numbers. Okay, so this is the Taylor extension of tangent. And, okay, then we have this. Oh, this is a real theorem to prove this. We have to play a game, we have to do something. So this has to be proved in some way. So in other words, remember what t 2n plus 1 was? Let me go back to here. You see? So when you plug q com 1 in the genic function for the doubloon by the compressed major, it's tangent. Oh, then you see, you have the reduce coming up. The reduce is those 1, 1, 4, 34, you see 1, 4, 34, 496 is simply tangent numbers divided by. They are still divisible by, there are still even integers in here, you see. But this is not the maximum divisibility by 2 of those numbers. And so, term 2 is really, if you have term 1, term 2, it's easy. I mean, that's the same. That's banal. So those are the reduced tangent numbers. 114, 34, and 496. Okay. Accordingly, okay. T is the Q analog of the tangent numbers. D and Q is the Q analog of the reduced tangent numbers. And where do they come from? Okay, oh yeah, I should have given maybe my notation before. See? So everybody agrees with, that's easy for everybody. I mean, that's the usual notation for the in Q series. So we have the QS factorial.
You kind of hesitated there.
What have I written here? Oh, it's written twice.
It's good.
Oh, that's good, you see, it's written twice. Look at this. The Q minimum coefficient, no problem, you see, so it's okay. So we can repeat, you see, it's already repeated on the screen. And, so, so Cornitz introduced in 1954 the Q analog of the union numbers. Not exactly, but we could say by this definition. In other words, let's start with this. This, Euler himself, well, he did not write it like this because, at the time of Euler, there was no sigma sign. So he could not write like this. Usually you write plus, 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 and dots, and etc., usually, etc. But actually, this is already in Euler. This is the way we read Euler today. And what Cornitz had done, Cornitz has replaced this by this expression. When you plug Q called 1 here, you have this. And this is, this stands for 1 plus Q squared plus Q to the J. This is 1 plus Q. And when you plug Q equal 1, you get this. So the miracle is, when you replace everything by the Q analog, you have a sequence of polynomials in two variables. And that sequence, that polynomial has positive coefficients, which is not obvious from this definition. This has to be proved, either analytically or using a combinatorial technique. So, and now I come to my point. Why we have introduced the Doubloons? Because, hopefully, oh yes, look at this. Give a table. You see, when you introduce a sequence of polynomials, you better write the first values. So this is coordinates. So this has existed for 50 years. It's not new. This is coordinates. So you see, these polynomials. Okay. Okay, let's go back. And then, this is definite theorem. So this is the definition of coordinates. And what happens is this. Look at this. Now, when you replace t, by minus q to the minus n, and you multiply by this, you come up with a polynomial with positive integral coefficients. And this has to be proved. So why, you see, why here, when t is replaced by this, here it's okay. I mean, we don't mind this. Is to make sure that we have a true polynomials in Q. And so this is exact. Okay. So and then we have this, and we proving this prove that the polynomials has positive integral coefficients because we have a combinatorial interpretation. Okay, so and let me repeat. So this is a definition of those polynomials in two variables defined by coordinates. We know that each of those polynomials have positive integral coefficients. And now when we replace t by minus q to the minus n and multiply by this, we still get positive polynomials with positive integral coefficients. And I think that no, this is not true. Now we have an analytic proof, but using the Doubloon model, we do have a combinatorial proof, interpretation, and a proof of positivity.
But T is still specialized, right? You're specialized T to...
No, not yet. Oh, T is not specialized. No, T has been specialized in minus q to the minus 1.
Yes.
Minus n.
I mean, could there be an interpretation with q to the sum C match times p to the sum other statistic, which exactly matches?
No, because I didn't mention here, first we have to prove that C match is always positive. I did not mention it before, but I should have mentioned it. But let me say, okay, look at this. So those are the genic function for interest doublets by C match. And here you divide, and here you two is so D3 is like this. So this polynomial is divisible by 1 plus q. This polynomial is divisible 1 plus q and 1 plus q squared. Oh, okay. Remember now. Okay, now I come to 9 minutes. 9 minutes. I have to remember 9 minutes. Remember 9 minutes. So, remember, DNQ is unique polynomial for normalized doublets by C match. Okay, now.